Good morning. Today we can say another single degree of freedom system when is applied an harmonic load. And we study his vibration. We can remember the system where there is the mass applied and force PT and is fixed with the spring and system undamped system C. So we can write using the second law of Newton this equation where there is the force, inertia force plus the damping force plus the spring force is equal of applied force PT. The inertia force is equal of mass for acceleration. The damping force is equal of C, damping coefficient for the velocity, and Fs is the spring force is equal K, the stiffness of spring for the displacement X. So the first equation we can write in this way: mass for acceleration plus C for velocity plus K for displacement equal of applied force PT. For the harmonic load or sinusoidal loading, the force is simplest dynamic force and frequently congruent in vibration to the machine. The nature of this force is well defined in terms of magnitude, frequency, shape, as well as duration. It is therefore customary to begin the study of dynamic structure with this loading. A single degree of freedom system is subject to harmonic load. Its response is studied without and with the damping force. Now we can study without damping force. The total response consists of two components: a transient response, which dies out quickly, and steady state response, which continues till the forcing function continue. The steady state response has a constant amplitude and frequency, and the ratio of frequency of forcing function and that of the structure plays a very significant role in dynamic. If the force frequency is equal to natural frequency of a freedom system, a resonance is said to have occurred. It is very enlightening to study the response at the response. So now we can say the case of an undamped force vibration. So we can simplify in this way, where there is only the spring and not the damping system. So if PT is equal to P0 for seno omega bar for T is the harmonic loading, where P0 is the amplitude of harmonic loading and omega bar is the circular frequency of harmonic loading. The second equation here we can write in this way, where C is equal to 0. So M for acceleration plus K for displacement is equal to P0 for seno di omega bar for the time T. Its solution is consistency of two components: the complementary solution, we can say in the last video, and the particular solution. Now we can study the particular solution. The particular solution means the specific behavior generated by the form of dynamic load. The response of harmonic loading can be assumed to harmonic in this phase with this loading. So xpt is equal to G for seno di omega t. Differentiating twice this so this differential this equation and put in the first equation, we can write this total equation, simplify sin of the omega t in the first second member of the equation. We can obtain the value of g. So g is equal of p0 divided for k, multiply for 1, divided for 1 when beta for elevated 2, where beta is omega bar divided for omega is ratio applied load frequency to the natural free vibration frequency. So the total response is the sum of complementary solution, a steady state solution. And we can calculate the value of AB, AB depend of initial condition. So the initial condition t is time is equal to 0. We can have the displacement and the velocity of this time. For if the system is rest at the displacement is equal to 0 and velocity is equal to 0, we can obtain the value of beta is equal to 0 and A equal of this quantity when P0 for beta divided for K multiply 1 beta elevated 2. So the final solution of the displacement xt is finally this four equation, where P0k is the displacement which will be produced by the load P0 applied statically. 1 so 1b2 is magnification factor, representing dynamic amplification effect of harmonically applied load. Seno di omega bar t è il response component the frequency of this applied load equal of steady state response directly related to the load. Beta seno omega t, a response component at the natural frequency of vibration is a free vibration effect induced by the initial condition. So the last term in equation 4 is also called the transient response. Transient response. This quantity. So we can plot this equation, and we can see there is the first line is the steady state response. This is the transient response, and the blue line is the total response. With this is the case of mass 253 kilonewton per second divided per meter. K is 7,500 kilonewton per meter. P0 is 100 kilonewton. Is omega bar 3.5 radiant per second. For initial condition of the displacement is equal to 0 and velocity is equal to 0. Now we can implement this equation with the Python code. We can see here the Python code. We can see line by line this code. The line 89 and 10 is there is the import of library. Import NumPy is NumPy. Is the standard library for numerical mathematical handling array. Scipy import odeint, import the function for scipy. This is power solver for ordinary differential equation. after import Matplotlib, is import the plotting module to generate the graph. After here there is the parameter of the figure. We can say trauma point 2 is the mass, m is the mass of the system, k is the spring constant in kilonewton meter, c is the damping coefficient, in this case is equal 0 because it is undamped, p0 is the force amplitude of harmonic force, 100 kilonewton. Omega bar is the frequency of harmonic force. Here they write the value of omega and the beta, and after we can write a function for solve the differential equation where define the physical system. xv equal zeta is unpack the current state vector zeta into displacement and the velocity. F calculate the exact value of the applied harmonic load of the current time. dx dt, the first derivative of displacement is the velocity. dt is the first derivative of velocity is acceleration. And this comes directly the Newton's second law, where there is the mass for acceleration plus c for the velocity plus k for the displacement is equal to ft. And return this function return the velocity and acceleration. Here in the line 55 define the initial condition, velocity and displacement at time 0 and velocity is equal to 0. And TF is total duration of a graph we can plot. So define a time t in the range 0 TF with the step 0.05, and z call the function we can with this parameter. So the total response of differential equation solved is equal to x total and v total, and we can calculate the equation of the acceleration, the total acceleration, and the force applied. Here in the line 54, 57, we can write the component of x steady and x transient, and after in this block 65, line 65, we can plot the displacement, the velocity, and the acceleration. And finally, in the line 91, we can plot the solution. So we can see the solution of this code, Python code, where there is the displacement, where there is the curve of a transient response, the steady response, the total response in blue, and after the velocity and the acceleration function of time. Finally, we can say an simulation of this system We can see the mass where is applied the force Pt in harmonic force, and we can see the displacement, velocity, acceleration, and the force with the elastic force, inertia force, it applied the force. Here there is the table with the value of system, of mass, stiffness, force amplitude, force frequency, naturally frequency. And after the initial displacement, the initial velocity, in this case, is equal 0. Okay, is all. Thank you. Bye.